So last week during the conference, we covered a lot about the US 85 and Long X Bridge project development. Today, we'll be going a little more in depth about the Long X Bridge replacement from a geotechnical point of view. We'll be going a little bit about some of the project background that we may not have touched on in the past, then talk about some landslide mapping, some of the instrumentation, what we found based on that information. Aaron will later talk more in depth about the soil properties encountered, the geotechnical design needed for the structure, and all the other in-depth analysis needed to ensure the new bridge is going to be designed to stand the test of time. So we saw this map last week, but I'd like to reiterate, you can see the east-west main 4-lane highways going through North Dakota and north-south. Over here through Watford City and down to Belfield, we're missing that last piece of the pie. So as we discussed last week, back in the early to the mid part of the 2010s, DOT decided to put into an action an analysis of how we could accomplish 4-laning this segment of the road. This was done due in particular to the increased oil traffic in the area, but as well as to allow for some interstate commerce, as the section of the road is part of the Ports to Plains Alliance with connecting Canada, USA, and Mexico. As things progressed, it was decided that like the first stage of this project was going to be to replace the Long X Bridge. The existing bridge was a truss structure that crossed the Little Missouri River through the Badlands area, just near the north unit of Teddy Roosevelt Park. Here in this slide, you can see a selection of some of the bridge strikes that have occurred over time and the damage caused to the structure. With multiple strikes occurring yearly, it was very apparent that the old Long X Bridge did not meet the demands of today's transportation needs. Now moving on to the geotechnical aspects of this project. As with any geotechnical engineering program you're going to develop, it's important to understand the geology of the area that you are going to investigate. As you can see from this geological map provided by the North Dakota Geological Survey, this area is riddled with mapped landslides. Now, just by looking at this map doesn't give you all the information you need to, develop a project through landslide riddled areas. And in order to determine that, a large geotechnical program was developed to identify geological hazards that would be present in any 4-laning of this section of the highway. Part of that process is doing a field investigation to help visually identify any geologic hazards that may affect the project. During a period from 2014 to 2015, a team from Shannon Wilson performed more in-depth mapping of key geologic features, such as landslide headscarps and toes. Here in the slide is an example of some of the geologic features that were identified. Areas that have been previously remediated during the original construction of the alignment during the 1960s have now shown signs of further movement. So with more in-depth knowledge of the area achieved through field reconnaissance, a detailed boring and instrumentation plan was developed. Through this process, some generalized recommendations were able to be made in specifics on how to create a reliable section of 4-lane road through US 85. If we zoom into the area of the Long X Bridge, you can see in the large yellow outlined area here, or on area 15 here, that there was it was apparent that this landslide here was affecting the old alignment of Long X Bridge and the new one. So borings and instrumentation were installed into the slide area, outside the slide area, and along the proposed alignment of the new bridge. It was important to install inclinometer casings in the area in order to have a better understanding of how the slide was moving and at what depths below the ground the surface was moving. I'm unsure of how many of you are familiar with how an inclinometer system works, so I'm going to do my best to describe it. For the type of installation that we used on this project, it consists of several things. First, you need to drill the hole into the ground to the desired depth that you want to measure ground movement. Second, you place what is called an inclinometer casing into the ground. Inclinometer casing is basically a hollow extruded plastic pipe with grooves at 90-degree intervals on the inside. It is important to line up one of the grooves with the expected direction of the movement that you believe is going on. Once the area around the tube and the ground is grouted in with cement bentonite water mixture that has a strength similar to the surrounding ground. Now that the casing is in the ground, we use a system that consists of a rod with accelerometers in it that can measure vertical displacement. The system is then lowered into the tube and measured at 2-foot intervals. It measures the inclination of the probe and perpendicular planes as to allow for the creation of a vector, which can give you the true direction of movement of the landslide. Over several leadings, it will show you how the inclination of the tube has changed over time. As you can see on the graph on the right side, over time it was apparent that this tube was experiencing movement at a depth of around 52 feet. So here the green arrows show the movement of direction in the ground that was detected during the study. The instrumentation that was placed around the south abutment of the old bridge and the new bridge did show that movement was occurring. Interestingly enough, the old Long X Bridge never really did show many signs of distress due to the earth movement occurring around it. However, anecdotal evidence that the old bridge was not experiencing distress due to the movement does not mean you should not take into account when designing a new bridge that is meant to outlive all of us. It was apparent that the south substructure of the new bridge were going to need to be evaluated to consider these further earthen movements. So with all the information that was gathered, a subsurface profile of the alignment of the new bridge can be created. Using this information will allow for a proper geotechnical design of the substructure for the new bridge. So I'll turn it over to Aaron now to discuss more.
Thanks, Matt. Let me pull up my other screen here. So as Matt indicated, we drilled all these borings. We create a subsurface profile. And now we know that this massive landslide is moving through 60 feet at a shear plane below the ground surface. So why is the landslide moving that way? Part of understanding the problem is you need to do soil index and shear strength testing. So generally for most projects, you'll do water contents, figure out how much water is within your soil, which is important for pavement design as well. You'll do index testing to see how much water it can potentially hold. And for this project, we needed to understand for the mineralogy how these soils were behaving so that they're sliding on these very shallow planes. So we did some X-ray diffraction testing to look at the actual clay mineralogy and better understand how these clay soils are behaving, as well as over on the right here, we've got a stratigraphic column. So the Sentinel Butte Formation is very nearly horizontal throughout this corridor. And part of what we did was throughout that whole area, we were able to do some testing, and we found that there were 4 main areas where we saw quite a bit of stability, and those were located with these green-gray claystone layers. So you can see we've got these different zones, and right at the bottom over down at the river is where we saw these clays where we were seeing movement at the Long X Bridge. And again, you can see here the axis is at, we've got liquid limits up over 200, which is pretty high if you're not used to dealing with these types of soils. So we also then performed strength testing. So for our landslide design, we can understand how the soil will interact with our structural elements we're putting in place. So triaxial tests are pretty common for foundation design. And you can see here we've got a nice shear zone along this sample. And from there we can come up with a compression test for getting a friction angle for peak strength, and then looking at the failure, something closer to fully softened. These landslides, though, as Matt was saying, there's a significant history of movement out here, and it's a different type of failure. So we subbed out and performed ring shear testing. So it's a unique device where you actually put in a remolded sample into this cylindrical apparatus. And the benefit of it is that after you apply your axial load, you can basically shear the specimen an unlimited distance. And for these landslides, since they've been moving for such a long time and over great distances, the clay mineralogy actually lines up with that shear plane, so they become aligned, and therefore your failure mechanism is much different than from a triaxial test where it's just a squish and done. This has moved hundreds of years over many feet. This is the failure mode you need to look at. And so you can see here on the graph we've plotted up the shear stress versus normal stress for this landslide, and we're looking at a friction angle of 7 degrees for design. And compared to our triaxial test, that was looking up at 30 degrees. So you can see it's a very different failure mechanism, and that's why we need to perform these different type of tests to understand how the soil is moving at these very shallow slopes. So once we understand our soil properties, we move into limit equilibrium analyses. So what's shown here is just a simple Geostudio slope stability analysis, and this is where you'll generally start. Your factor of safety for this landslide is right at 1, meaning it's just barely staying stable, and it's slowly creeping along. So this is generally where we'll start to understand the geometry for causing these failures and what needs to be done in order to put our bridge in place. From there, we move on to numerical modeling. Because we're dealing with such an important asset of a bridge, we need this abutment to function through this landslide. So what numerical modeling just basically is it looks at soil structure interaction. All of these units here shown, this is for a different project, also working on in North Dakota, but basically when you reduce the soil shear strength, you see a resulting deflection within your structural elements. So you actually model the reinforcement within the drilled shafts. We also usually put in ground anchors to help tie back the drilled shafts at the top. And you can, from there, complete your structural design, understanding how this landslide is imparting loads onto your foundation. So here's just what a typical output would look like from a 2D numerical model, and you can see this black line here is our moment curve through the drilled shaft. For this project, the landslide was of such a scale, as Matt was talking about, that we worked with the DOT, and our solution was not to stabilize the entire slide, but to resist the loading at the bridge location. So this model is showing the 3D entire landslide, and what we've got over here is the cap beam. And then we've got ground anchors going back, and part of this is that the model is cut in half right at the middle of the bridge, basically. And the reason we do that is just for symmetry. These models take a while to run. Some of the ones I've run in 3D take up to 12 hours. So if we were to basically double this model and make it symmetrical, we're basically modeling the same thing on the other side, but we can cut our modeling time in half by assuming it's symmetrical across the bridge. So taking a closer look at what this looks like within the FLAC 3D program, where we get into 3D modeling, we can see we've got drilled shafts modeled here. So those are, not only acting as axial members for supporting the bridge abutment, but they're also resisting the landslide loading, where you've got the soil pressures down to 60 feet that are pushing into the river. So the drilled shafts are tied into a cap beam, and then we've got ground anchors, which are basically steel tendons that are drilled through, installed through the abutment, and then they're grouted up and tensioned. And what that does is that pulls back the cap beam and helps pin the drilled shafts at the top so that they initially resist some movement and then work in tandem with the ground anchors to resist some of that landslide loading. And what was really interesting about our solution working with the DOT for the Long X Bridge is you can see there's this additional drilled shaft off to the side. Because we're not fully resisting the stabilizing the landslide, we're allowing the landslide to move along the side of the bridge. And because of that, we have this extra drilled shaft here, which takes a lot of deflection, but basically it acts as a buffer so that this drilled shaft can deflect. It's not tied into the bridge, and it can bend as much as we need it to. And that reduces some of that landslide loading before you get to the bridge. So if basically all of the drilled shafts were tied in, we'd have a much higher load that we'd have to resist because it's taking the full brunt of the force. But with this 3D problem, we were able to have this sort of sacrificial drilled shaft kind of bear some of that load and help reduce the load within the bridge. So here's, once you start running the model, you can see here we've got our displacements down towards the river. So this is upslope, this is downslope. You can see we've got our anchors pulling back there, but basically these areas of orange contours are showing displacement of almost up to a foot with our soil reduction. And then at the bridge where we've got the drilled shaft elements and the ground anchors, you can see that we are limiting the deflection for design. But with that, since we're limiting deflection, we end up with a lot of stress within our structural elements. So from there, we're able to look at how these drilled shafts are bending. We can look at the axial loads within the drilled shafts. And from there, just through structural equations, we can correlate that to shear and moment diagrams. So basically, we take all of that geotechnical side of it, but then we're able to come up with something, a structural engineer can easily work with and design for the loading for these drilled shafts. And you can see here, the max factored moment is 18,000 kip feet, which is pretty enormous to resist this landslide down to almost 60 feet. And with that, we have, even with those very stiff elements, we're still estimating surface deflection of over 4 inches. So with this, we were able to work with the NDDOT. The DOT did all of the structural design for this abutment, and they designed the abutment to tolerate up to 6 inches, I believe, of movement. So here's the layout of the bridge. You can see just from south to north, all the other locations are not impacted by landslides, and we have just simple pile cap for each of those. North abutment is also just 2 rows of piles, but here at the south abutment, you can see we've got these massive drilled shafts. Only 5 of them in the middle are actually supporting the bridge. The 2 on the outside are sacrificial, not tied in, so they're allowed to bend. You can also see from this little photo here, we've got those solar panels. That's our instrumentation I'll talk about in a bit as well. So I just want to quickly touch on the construction because these drilled shafts were pretty unique. So again, these were 8-foot diameter, 3/4 inch thick permanent steel casing for the full length. And that's what we're looking at here is the steel casing that's used not only to provide bending, but it also helps provide stability for the drilled shaft while you're excavating. Quite a bit of reinforcement. They were up to 127 feet long on the outboard side, which ended up to be significant concrete pours. We also had 2 movement sensors installed to monitor deflection of our drilled shafts. So hopefully this video is coming through a little bit, but when you're out there, it's pretty slow going. This oscillating rig actually advances the steel casing with its weight alone, along with hydraulics, down into the ground. So they had 2 pieces of steel casing, and they would then, once they got this first one all the way down, they'd pick up another case, put it on, weld it, and then continue pushing casing. Normally with drilled shafts, you have an auger, but for this system, because we're advancing with casing and you can't get an auger when you've got 70 feet of casing in the air, they use this clamshell bucket. So the casing has teeth at the bottom, tears up the soil and rock, and they're able to pick up the soil with this clamshell bucket. So what was kind of interesting is the contractor at first struggled with a layer of lignite they hit, which is harder than a lot of the surrounding claystone, but once they figured out how to get through it, they were making good progress. So this is the reinforcement cage they put inside the excavation once they push casing all the way down. And it's just pretty cool to see these guys in the man basket, what level they're on compared to the rest of the reinforcement cage. It's just, it's a massive reinforcement cage, but that's what we needed to resist the landslide movement. And that first drilled shaft, it was about a 16-hour day on site. But that's kind of how all the first drilled shafts go, just long days. But here they are wrapping up the pour, placing concrete via tremie, pushing out all the excess water that was inside the shaft. And this first shaft took quite a few days, but once they got in the rhythm of it, the rest of the shafts followed pretty smoothly. So once they get the abutment in place, then they're putting in these ground anchors, which basically, like I said, they drill with air and water. They use this steel casing to stabilize the excavation while they drill it. And then they feed in a steel tendon, grout it up, and then they're able to tension that back to resist some of that landslide loading. So what we're looking at here is the sacrificial test, where basically we can load it up to twice what the production anchors will see. So we can see what the soil is capable of fully holding. We use a bigger anchor and we load it up to its full ultimate load. And that way we have the confidence we can throw on a factor of safety to our production anchors and not worry about overstressing the anchors that are within the abutment. So here they are feeding in the steel tendons downhole for the sacrificial anchor, and now we're testing it. So basically with the testing, what they do, they have this hydraulic ram, they pull on the steel tendons, and you're basically trying to pull the anchor out of the claystone. So if they apply a load and it pulls out too much, they failed. We need to evaluate our design, but fortunately, these anchors performed very well. Here we're monitoring the elongation. We also had downhole sensors, which that way you can see how the stress is transferring throughout that bond zone. And we had a very successful sacrificial test. All of the production anchors were installed. Similar methods, very successful over there. This was also a great opportunity. We worked with the contractor and the DOT to get a sacrificial test for Horseshoe Bend, which is an additional landslide up the road. The bridge is down there. But from this, we were able to get a test ahead of time and dramatically reduce the ground anchors we needed for this stabilization project. Because we were able to get out there ahead of time, we were able to cut down our factor of safety. We have this information ahead of time, how these anchors will behave, which they did pull out a little bit more than at the Long X Bridge. But with that, we were able to save the DOT a significant amount of money ahead of time during design by getting this information and increasing the confidence in our design in order to stabilize this landslide. So just looking in, here's where our sacrificial test was over to the side, and you can see we've got these blockouts for the production anchors. Zooming in there, you can see that's where the anchors are actually put in to tie back the cap beam and to resist the landslide loading. So again, okay, we have these massive foundations, you know, like Matt said, what's happening? Well, we instrument them and we've already seen movement to date. So you can see from the scale here, we're only talking about 0.2 inches, but still when you're talking about 8-foot diameter shafts, 130 feet deep with permanent steel casing that are already deflecting, there's a reason we go through all of this exploration and design to resist this landslide that's there. And again, I'm just bringing back our design of over 4 inches, showing that 0.2 inches, it's moving, but we got a long ways to go before there'd be any cause for concern. Yeah, so this shaft, I should say too, this was one of the sacrificial tests on the outside, moving 0.2 inches. The one at the center of the abutment, it hasn't even moved, 0.04 inches because it's tied back by those ground anchors and it's actually in the center of the bridge. We have ground anchors too that we're monitoring. You can see this movement here is actually from contraction and expansion probably of the bridge. We're not sure, but that's what we've seen on other projects, and we'll continue to monitor it and see if that ground anchor relaxes throughout its life. So just some quick conclusions. To understand these geotechnical hazards, there's quite a bit of additional exploration that needs to go in, laboratory testing and instrumentation to fully understand the problem. As Matt was saying, this area has had consistent issues, along the corridor with slope instability. And it's important that when you're putting in such a large asset, you understand the problem correctly the first time and you design something that will last through its service life and hopefully more. And with that, you need to get into some more numerical modeling for design because that 3D soil structure interaction can be very important depending on the problem, especially this unique situation where we were able to work with the DOT and figure out a design solution where we're not fully stabilizing the landslide, but resisting the loading. And finally, kind of tying back into some of the conclusions from the pavement, but instrumentation, and extra monitoring for during construction can save you a significant amount of money protecting these large assets you're putting in for transportation, and you're also getting better data for future projects. So We're really creating a good database here for how these bedrock and soil samples are behaving, and that all provides value for future work. So anyway, thank you. If there are any questions, hopefully we can answer some. If not, please reach out to me and Matt after the presentation.
All right. Thanks, Aaron. Thanks, Matt. Great presentation. Another presentation that's talking about protecting our assets, and so I think we got a theme started there. There is one question that came in through the Q&A, and I would encourage anyone out there that's got more questions, please drop them in the Q&A box. But one of the questions was there any anomalies encountered when they were installing the drilled shafts?
Yeah, so that's a good question. With the permanent steel casing, I wasn't too involved with this. I think the structural folks could speak to it. But when you introduce permanent steel casing, you reduce the chance to get an anomaly significantly because you're fully stabilizing the excavation. There's no chance for groundwater to infiltrate during concrete placement. And really the only anomalies that would form are from poor concrete placement from, let's say, from the plant not meeting strength or something like that. There were some suspect tests. These were instrumented with cross-hole sonic logging things where they basically are able to see this velocity of the concrete. And there were a few suspect areas. They were right at the top of the shafts, so we were able to core those, and those breaks performed satisfactorily. So because of that permanent steel casing, again, these large drilled shafts were able to go in without much of a problem at all.
One question, maybe just elaborate a little bit more on the cross-hole sonic logging, and as far as an inspection tool, when you have a 130-foot long drilled shaft, you can't see the bottom of it. You don't know what's going to happen down there. So can you explain that a little bit further?
Yeah, for sure. And I want to say too, for as tough as drilled shafts are, ground anchors are 10 times worse because, again, you can't see anything at all. And with that permanent steel casing, it's the same thing. It's sticking way up in the air. All you can log is what the clamshell bucket is taking out. But once they get the drilled shaft to its final depth, you can use, they cut off the steel to where it needs to go, and we were able to inspect and see with a mirror if there's any groundwater infiltrating in, as well as sound the bottom with the steel tape. So we were able to inspect these shafts, and Braun Intertech was out there full time doing the inspection. But that steel casing, again, helps us make sure that we get a good solid stabilization while we're excavating for these.
Okay. One more quick question on you talked about the challenges of ground anchors, but what's the process for anchoring a ground anchor into the developing that bond length that you need?
Yeah, I could talk about that for half an hour on its own, but basically those anchors are sent out pre-manufactured from the plant, and they have that bond zone that's built in inside that corrugated pipe, and then they basically grout up the outside of it. So within the bond zone, it's already pre-manufactured to have intimate contact with the steel tendons, and then within the landslide area where we want the anchor to elongate, it's greased up on the inside. So it's a lot of working with the plant to make sure that they send out those anchors, and then the contractors grouting them up appropriately during construction.
Okay, I'll try to get to a couple more questions here quickly that has come in. Based on the rate of movement observed thus far, is it safe to assume that in 21 years we could see deflections up to 4.3 inches?
Well, that's a tough question. Maybe Matt can jump in for this one too. But in 2011, there were significant movements. It really depends on what type of precipitation you're seeing and how these landslides change over time. Do you want to jump in, Matt?
I think one thing that we had some inclinometers in that Painted Canyon project that we did, and early on, at about the first year, we saw some deflections backwards, but over time they seem to stabilize. So I think it was a similar type fix there. I think you might see some movement initially, and then probably slow down over time.
One more question. for you guys. What is the cost of the shaft abutment compared to the standard pile supported abutment?
I am the wrong. Roger would be good to ask. I think he knew the cost, but I mean, each drilled shaft alone, I think, was over 100,000. Just because, again, this is specialized equipment. The concrete pour itself is 220 cubic yards, and that first drilled shaft took 7 days to install. So once they got the hang of it, they went faster. But the abutment itself, yeah, it's not a cheap fix. But again, that's why we instrumented and we're able to monitor it.
Yeah, I think that's a good way to characterize it. You know, without having those costs at the tip of our fingers, it's significantly more expensive than a pile supported foundation. But the solution called for that. If you remember from Dustin Wing's part of the presentation last week, we were also able to shorten the length of the bridge. So there was a fair amount of cost savings involved by shortening the bridge about 190 feet and then installing this kind of abutment. So it's kind of an overall solution that has to be evaluated both from the structural design, the geotechnical design, and other considerations. So